Let's talk a little bit about combining like terms. Now, I'm going to use containers like baskets, bags, and boxes to explain like terms, but I'm going to have a few fruit floating around, some apples. Now, a lot of teachers use like apples and oranges to explain it. I don't do that. And the reason I don't, and I think it's wrong, is because I went to a conference about 20 years ago, and this great explanation of why that's such a weak way to explain it. It's so much better to explain it using containers. So let's set this up for a bit. Let's imagine we have a bag on one side, and then we have a couple apples sitting there too. And then, as it turns out, they're on a balance. So, what do you know is inside the bag? What would be inside the bag if these two things are balanced, so therefore they're equal? Doesn't it make sense that there's two apples inside the bag? Sure, that makes sense, right? What about this image? I've got a box is equal to 4 apples. What's in the box? Well, of course, it's 4 apples, right? So the box is holding 4 apples, and we knew that. So now let's actually use a variable to explain this. So if we have a bag and it's equal to 3 apples, let's define the variable x as being the number that's in the bag. So if I get rid of the other side, what is x? What's in the bag? Well, of course, remember it was 3 apples, so x is 3. So the number 3 is represented by the letter x here. So x equals 3. So let's start again. We've got a basket, we've got a bag, and we've got a box. Now, how many apples are in each one? Well, of course, we have no idea, right? But we could start to label some letters. Remember, inside the bag, we could call X, and we could label the basket Y. We could label the box Z, right? So how many total apples do we have? Do we know? Even doing this, we don't know, but we could describe how many total apples we have. It is x plus y plus z, whatever the heck that number is. This is called an expression, and it shows you how many total apples there are on the screen right now. Now, we don't know what's inside, but we do know that the total would be x plus y plus z. All right, so let's take a look at this. We've got 2 bags, and in each one there's x, and the whole thing, therefore, is, of course, 2 bags, right? 2 times the x that's inside each bag, so 2x. Now, in world of algebra, we just write 2x, 2 times x, and of course that came from x plus x. So x plus x ends up being 2x. So if we had x equals 3, for example, you see how I've got 3 apples in both bags. That would be 2 times 3, which is 6. So we have 6 apples entirely. So 3 plus 3 is 6. X plus x is 2x. Notice there's no x squared there, folks. We're just describing these groups of x, whatever it happens to be. In my example, I went ahead and put in 3 apples, but it could have been anything. We really didn't know until we were told. All right, let's look at another one. What about this? If we have 2 baskets, and then someone brings in 3 more, and we group it all together, what do we have? Well, we've got 2y plus 3y, don't we? We had 2y, whatever's inside, we're calling it y, and then we added 3 more. So how many total groups of y do we have? We have 5 groups of y. So 2y plus 3y is 5y because y represents a number. It's a number of mystery apples that are inside these baskets. It's not just a fruit. All right, it wasn't 2 apples plus 3 apples equals 5 apples. They were actually basket because they're holding a mystery amount. Now let's just start with the algebra this time. So we've got 3z plus 4z. What do we get here? Well, we've got 3 containers, and then we add 4 more. We have 7 containers. So 7z total would be our answer, right? 7z. Okay, let's switch gears again. On a table, there's 2 bags sitting there, and there's a mystery amount in both of the bags. Now, they're the same, so they're both labeled X. But also on the table are 5 apples. You see them there. Let's write an algebra expression that describes these two things. So we said before that the 2 bags is x plus x is the same as 2x. And then what else do we have on the table? It's not 5y, it's not 5z, it's just 5. It's just 5 apples that were not in a container. So 2x plus 5 would be our answer. That's called an algebra expression. Okay, so that was a lengthy way to set the table for the next question. We are going to combine like terms. So here we have how many terms? There's 6 terms. Going from left to right, if you count them, they're all positive except for that -1 is negative. So we have 6 terms, and we're going to combine the like terms. So it's the bags and the boxes and the baskets and all those different things. So let's identify the like terms. I see that there's a couple of x's, right? So 2x plus 4x gives us 6x. What else are like terms? The y's. I see a 3y. I see a 5y. Remember, those represented the baskets, I think it was. So we've got 3 and 5 means we have 8y, not 8y squared, right? You see some of your friends do that sometimes, right? But it's just 8y because it's 8 baskets. And then -1 plus 2 is +1. The positives win by 1. All right, so here's another example. 3x squared plus 5x minus 3x plus 2. All right, so let's combine the like terms. You see any like terms here? I see a couple of x terms. I see a 5x and I see a -3x. So we could go ahead and combine those. Now, what about the 3x squared? Well, that's its own kind of container. So that might be a tube or something else, some other shape. Think of it as being different, okay? A different holder. It's a different type of term. So there's nothing we can do with it other than bring it down. But the 5x and the -3x will combine to be 2x. And then at the end, we have a +2. And it doesn't have any like terms, so that is our final answer. I do often get students who write 7x to the third at this point. And of course, I cry a little, shed a little tear there when the students do that. So this is the answer because there are 3 different types of terms. There's an x squared, an x, and a 2. All right, I've got another example here for you. I think this is the last one I have queued up. Look at this. We have a 4-term polynomial, it's called. It's got an x to the third, an x squared, an x, and a 5. So there's 4 terms, and they're all unique types. So they're all different shapes of containers. Now, what if we bring in another 4-term polynomial, 4 more terms, and I say, hey, you know what? Hey, let's add these up and combine like terms. Okay, well, notice how I've lined everything up for you. That was really nice of me. So what about the x to the third? -x to the third, and then +2x to the third. Well, that's just +1 x to the third. I didn't put the 1 there. You can if you want. Notice it's not x to the 6th. We do not add exponents. Why? Because we're just describing containers. These are variable expressions, and we plug numbers in. There's a mystery number hiding in that container. We just don't know what it is. All right, let's look at the x squared. We've got 2, and we've got -5. That adds up to -3x squared. And then how about the x's? I see a +8x. I see a +x. You add those up, you get 9x. And then I see a -5 and a 2. Those are called like terms. We add them up, and we get -3. Well, what do you know? That is our answer right there. All right, so we've talked about combining like terms, and I use the analogy of a basket, a bag, and a box, and some apples sticking around. And we had all the different types, didn't we? We had x, y, z, or on these last couple problems, we even have x to the third, x squared, and x. I just need you to think about that as separate containers, and hopefully you won't make the mistake of adding exponents, because you didn't see me add any exponents today. That's important to understand when combining like terms. All right, well, hopefully you found this video useful, and now you know how to combine like terms. All right, check out my other videos, including I just did one on adding and subtracting integers, so that might be helpful for you too. All right, good luck, and until next time.